Hello, my name is Ann Webster, and I'll be sharing the results of our ESA Remote Sensing for Marine Litter project on behalf of the MDA team, Detection of Ocean Litter Plastics with Hyper-to-Multispectral Infrared Neural Networks, or DOLPHIN for short. MDA is a Canadian-owned and operated space company with a 50-year history developing advanced technical solutions for the space market. Our main business areas are grouped into satellite systems, robotics and space operations, and geointelligence. The effort I will describe today is part of our work to incorporate the latest in machine learning in our solutions to geospatial intelligence challenges. Successfully mitigating the damage caused by marine litter requires large-scale, accurate mapping of ocean-borne plastics across the globe, a task well-suited to space-based platforms. Plastics commonly found as litter have spectral absorption features in the shortwave infrared, or SWIR. SWIR hyperspectral imaging sensors can detect these plastics, but there is a lack of currently available spaceborne hyperspectral sensors for the task. While the current spaceborne SWIR multispectral sensors contain some of the key spectral ranges for plastic detection, the wide bands cause entire spectral features to be captured in single bands, making it more difficult to detect plastics reliably. In this study, we develop and begin assessing a neural network approach that learns to associate multispectral data with full hyperspectral absorption features so that single multispectral images can be used to detect plastics more reliably. The algorithmic framework developed by the team at MDA creates a joint plastic spectral embedding space between multispectral and hyperspectral pixels. To train this JPS embed algorithm, we encode matching hyperspectral and multispectral pixels to the same latent feature space. We then use a classifier composed of dense layers on these encoded pixels, allowing for the identification of pixels containing plastic. The encoder and classifier are trained jointly to ensure the optimal encoded space for plastic classification. Once the JPS embed network has been trained, it is capable of taking only multispectral pixels as input at inference. The output plastic detection map contains values between 0 and 1, representing a probability that the pixel contains plastic. To train this approach, we require pairs of corresponding hyperspectral and multispectral pixels captured at the same time. In the absence of this type of data for the study, we leverage simulated data and consider plastic land targets along with the other synthetic materials to serve as proxies for plastic debris on shorelines. Establishing the approach with these types of targets is foundational for it to be expanded to work with floating marine debris in the future. We select AVERIS and Sentinel-2 as the two sensor sources with easily available open data to gather in-scene mean reflectance and covariance data used as the basis of our simulated data. We select several scenes from 4 California locations to gather a variety of material types, both synthetic and natural. Our simulation model assumes that the spectral distribution of every material follows multidimensional Gaussian statistics. We simulate pixel pairs consistent with the statistics gathered in real scenes to create realistic pixel values. We create both pure and mixed pixel pairs, assuming a linear mixing model of up to 3 different material types for the mixed pixels. We divide our data into training and test pixels to quantitatively evaluate the approach and qualitatively assess on real Sentinel-2 data. While we have no firm ground truth in the real scenes, we can identify some known plastic targets such as greenhouses and visually compare to gain insights on performance. We run the standard precision, recall, and F1 score metrics on our test pixels and compare the results to a maximum likelihood classifier trained on multispectral pixels. We confirm that our approach significantly outperforms the traditional one. We see excellent performance in the baseline dataset with an F1 score of 88.8% and note an improvement to 90.5% when we add more material types collected from spectral libraries such as vegetation and other plastics. We also note that when we reincorporate materials identified as false alarms in the real test scenes back into the training, we do not see overall increased performance from our quantitative metrics, but we do see a noticeable difference in the real scenes. Here we show an example of the qualitative results on a Sentinel-2 scene in Carpinteria, California. We identify areas with known plastic greenhouses with orange arrows, though the scene likely contains other plastics, including rooftops. In the baseline result thresholded at 0.5 on the bottom left, we see the detected greenhouses, but also note many false alarms in the surrounding mountainous and vegetative areas. We see improvement in false alarms when the algorithm is trained with additional spectral library materials and with false alarm mitigation, which consists of adding simulated materials consistent with some of the false alarms from this scene. When we threshold the output values to 0.9 instead of 0.5, as shown on the right, we also see fewer false alarms, and the plastic greenhouses clearly stand out. In summary, given the success of JPS Embed in this preliminary study, we are optimistic in the feasibility of the approach for land-based and shoreline plastic detection. We have demonstrated that strategically adding specific material types can reduce false alarms. Future work is needed to confirm the feasibility and refine the approach for operational quality results and for transferring the approach to open water plastic detection. Future work should also include incorporating real pixel pairs in training and testing and expanding the approach to sensors beyond the Copernicus Sentinel-2 case studied here. The authors would like to thank Paulo Corradi and Isa for their support in this project. Thank you for your attention, and feel free to contact us should you have any questions.